Share screen. Okay, so let me get started. And first of all, I apologize. Somehow last time I wasn't really watching time, so I went way over time. So I have to go backtrack a little bit and start anew on the Klein-Gordon field theory. So let me try to do that. So we did start to look into the Lorentz invariant quantum field theory, which was actually the first kind of quantum field theory people studied. And we spent a fair amount of time talking about non-relativistic quantum field theory in order to make connection to multi-particle quantum mechanics to quantum field theory with identical physics content, but nonetheless, it's much more powerful formulation. But when you go to Lorentz invariant theories, it's not an option anymore. So the QFT is really forced on us. And so that's the point I wanted to get across first. The first thing we discussed on last week about Lorentz invariant the quantum field theory is that first of all, we wanted to come up with non-relativistic quantum mechanics and relativistic quantum mechanics. So the question is, can we make quantum mechanics and Schrödinger equation in a way that's Lorentz invariant? And of course, the naive guess is we follow the same rule, namely that the energy in quantum mechanics is IH bar time derivative, and momentum in quantum mechanics is H bar over I, the spatial gradient. And what we did with the non-relativistic Schrödinger equation, which you have done in quantum mechanics class, is to replace this kinematic relation that kinetic energy is P squared over 2m by using these substitutions. And that's how we came up with the Schrödinger equation. And of course, you all know this story, cool. So one idea is to use the relativistic relationship between the energy and momentum, that E squared is P squared C squared plus M squared C to the fourth. And if you do the same substitution you have done in relativistic Schrödinger equation, so E squared turns into minus H bar squared dt squared, P squared turns into minus H bar squared grad squared. So that's how you end up with this equation. And this is the equation called the Klein-Gordon equation. So there's nothing wrong with this. This is a perfectly good equation. It's a wave equation of some kind, which is manifestly Lorentz invariant, because the time derivative squared and spatial derivative squared combine together to form the Lambertian, namely box. So I did mention that the box is referring to 4 dimensions because of the 4 corners, as opposed to the symbol for Laplacian, which is a triangle, which refers to 3-dimensional space. So this box contains both time derivative and spatial derivative in such a way that this is actually manifestly Lorentz invariant. So Klein-Gordon equation is a perfectly good equation as a candidate for the wave equation in a way it's that Lorentz invariant. But there was a problem, namely that it didn't allow for the probability interpretation like what we would like to have for us to have an analog of the Schrödinger equation. The main difference is that this equation is second order time derivative. So if you actually take the usual probability density phi star phi, which you used in quantum mechanics, you want the phi star phi, once you integrate over the entire space, to be conserved, because the probability has to stay 100%. And that's the requirement of unitarity in quantum mechanics. But when you take phi star phi and integrate over space, and take the time derivative of it, it's not 0. And that's because once you have the second order differential equation in time, phi at a given moment, and also its time derivative at a given moment, are independent initial conditions. And that's something you are familiar with the conventional Newtonian mechanics, namely that you specify both initial position and initial velocity to specify the trajectory of the particle later on. So phi and phi dot are independent initial conditions. So if you take phi star phi and take time derivative, then that's not necessarily 0. So most of the time it's not 0. And therefore you don't find the conserved probability in a way you want to allow us for a probability interpretation of this wave equation. You can come up with something that is conserved, and that's something you're actually looking into in your homework problem. So if you define this current J mu, which is again manifestly in the Lorentz covariant form because it's written in terms of this derivative with respect to x mu, And so this really does behave like a Lorentz-4 vector. In the time component, actually turns out to be conserved, and that's n you're looking into in a current homework problem. So you can find something that's conserved. But what you see here is that there's a minus sign in the middle of this expression. So the time component of this quantity is conserved, but it's not positive definite. And if you want to have a probability interpretation, of course, probability has to be positive semi-definite, otherwise it doesn't make sense. So namely that you cannot come up with something that satisfies two requirements, something that's conserved and something that's positive semi-definite. And in Klein-Gordon equation, you can come up with such an object. So the probability interpretation fails for the Klein-Gordon equation. So this is what I told you already last week. So that's why we cannot use Klein-Gordon equation as a replacement of the Schrödinger equation. So we have to abandon that idea. And instead, we take this wave equation as an Euler-Lagrange equation of a field theory, and then quantize this field to see what comes out of it. And that actually turns out to be a well-defined correct theory that describes a relativistic spin zero particle called the Klein-Gordon field. So that's what I like to do next. But anyway, any questions so far about these arguments? You want to come up with a relativistic wave equation. And we did come up with a relativistic wave equation, but it didn't allow for the probability interpretation. So this is not a relativistic version of quantum mechanics. That's why we are now forced to go to quantum field theory. So any questions about that? Everybody happy? Okay. So we have this wave equation now, which cannot be regarded as a relativistic Schrödinger equation. So we want to come up with a Lagrangian whose Euler-Lagrange equation reproduces this Klein-Gordon equation. So we need to come with a Lagrangian, and then once we have a Lagrangian, we want to quantize it. So that are the steps we're going to take. And it turns out that this is the correct Lagrangian. And it's easy to see why this actually reproduces the Klein-Gordon equation. First of all, it's important to know that the action, which is the time integral of this Lagrangian, is manifestly Lorentz invariant. So integration volume is three-dimensional space and time. So you integrate over entire four-dimensional space-time. So under Lorentz transformation, this integration volume is invariant. And if you look at the integrand, the first term has the Lorentz index contracted between upper and lower indices, and that's exactly how you build Lorentz invariant. There's no free index left. So this is guaranteed to be Lorentz invariant, which is good. And second term has no index to begin with, and this is purely Lorentz invariant from the beginning. So integrand is also Lorentz invariant. Integration volume is Lorentz invariant. Integrand is Lorentz invariant, and therefore action is manifestly Lorentz invariant. So we are basically guaranteed to come up with a Lorentz invariant theory out of this action. So that's good. Then looking at this action, then you can take the small variation with respect to, let's say, phi star. And you have been through this exercise already many times, so you can probably check by your eyes that when you take variation with respect to phi star, you want to act this derivative del mu, act on the rest by doing integration by parts. So that gives you minus sign. And then del mu is the box. So the variation, the first term gives you negative box phi. And second term, again, you take the variation with respect to phi star. So remaining stuff is negative m squared c squared h bar squared phi. And I cancel negative signs from both terms, and that's how we recover the Klein-Gordon equation. So this is the way you can easily check that this action is what reproduces the Klein-Gordon equation as its Euler-Lagrange equation. So that's exactly what we wanted. So then the rest of the exercise is to go ahead and quantize it, following the same rules we have used for the Schrödinger field and also for the vector potential for electromagnetism. So the rule of the game is still exactly the same. You first identify the canonically conjugate momentum to phi, you set up the canonical commutation relation, And you go through the mode expansion to identify creation and relation operators. So these two exercises are exactly the same as what we have seen already before. So that's what we would like to do next. So any questions about this action derivation of the Lagrange equation? Okay.
Yeah, I have a
Okay,
question.
go ahead.
So when you said this Lagrangian turns out to be in the form, did you find the Lagrangian so that the Euler-Lagrange equation becomes this Klein-Gordon equation, or did it come from somewhere else?
Yeah, so this Lagrangian had been basically, we basically came up with this Lagrangian in order to reproduce the Klein-Gordon equation as an Euler-Lagrange equation.
Okay, so we made up something that fits with this equation. Okay.
But you can also argue that this is the natural Lagrangian to start with in the following way. So once you have this field phi, then the second term is just the phi star phi. That's a quadratic term we have also seen in the Schrodinger field equation. So you can come up with that. And then you also would like to have derivatives. Otherwise, the system doesn't have dynamics with it. So having a derivative always means that something can change as a function of space and time. So you would like to come up with something that has derivative in it. But derivative with respect to four-dimensional coordinate forms a Lorentz 4 vector. So it has an index mu. So you need to come up with a way of contracting this index mu to build a Lorentz invariant integrand. And so this is the first thing you can think of in order to do so. So if you want to write down Lorentz invariant Lagrangian density as an integrand of the action, basically this is the first choice you would probably come up with. And you can also add terms like phi star phi, which leads to the self-interaction among the field phi, like what we have seen in the case of Schrodinger field theory. And so you can put that in, but that is an interaction term. So to the extent that we are only interested in a free particle for now, then this is it. So based on the Lorentz invariance and the requirement that you have the terms up to the second order derivative, this is basically a unique Lagrangian you can come up with consistent with the Lorentz invariance. So that's a sort of modern idea. So I took sort of a little historical path here and tried to sort of derive the Lagrangian backwards. But as I mentioned some time ago, the modern view is that you first start with a symmetry. In this case, symmetry is the Lorentz invariance. And you try to come up with the Lagrangian or action that is consistent with that symmetry. And to the second order in field, and only up to the second power in derivative, this actually is the unique Lagrangian you can come up with, consistent with the requirement of the symmetry. So even though we derive this backwards, if you go from top-down argument, this is the unique Lagrangian you should consider, which turns out to give you the Klein-Gordon equation. And that's the way we tend to think about this in the modern days. Okay, does that answer your question, UK? Okay.
Yeah, thank you.
Good. Any other questions here? It's a very good question. Thank you. Okay, so now we'd like to quantize this. So we first write this Lagrangian explicitly in terms of time derivative and spatial derivatives. And once again, once you have a lower and upper index mu, you use the metric to contract the indices. So the spatial component have the negative sign coming from the time space component of the metric. In time component, the time comes with a c, speed of light, to make sure that has the same dimension as a space. So that's how you can write out the first terms explicitly. And second term is, of course, already there. So this is the form of the Lagrangian we like to quantize. So the first thing is to identify the time derivative of the field phi and take derivative with respect to it to identify the canonically conjugate momentum. So that's clearly 1 over c squared phi star dot. And there was a typo in a homework problem where I didn't have star or dagger in it, so I corrected it. So if you haven't seen the latest version, please look at the latest version on the B courses. So this is the canonically conjugate momentum to the field variable phi. So we set up the usual canonical commutation relation between them. And once you have the canonical commutation relation, we like to identify the creation and annihilation operators, like what we did with the harmonic oscillator. So the phi plays the role of x, phi dot plays the role of p. So you write out the mode expansion in a way that phi is a plus a dagger. But in this case, we're talking about complex field, which is not necessarily real. So a and a dagger may be independent from each other, and that's why I'm using this symbol B instead. So I have AP as an annihilation operator, B dagger as a creation operator. And just like in the case of harmonic oscillator, if the x variable is a plus a dagger, the p variable is a minus a dagger. So it's the same way here. So that's the way the phi and phi dot as independent initial conditions would allow you to define a and b dagger in this mode expansion. So far, I'm exchanging two variables, phi and phi dot, in terms of two variables, a and b dagger. But the point of writing it this way is that then the commutation relation, it turns out to be exactly what we want for creation annihilation operators, namely from this equation, phi dot commutator. And of course, I also have the Hermitian conjugate version of this, phi dagger, 1 over c squared phi dot, has also the commutator, IH bar delta x minus y. And using those two canonical commutation relations, I can work out what the commutation relation should be between A dagger, B, and B dagger. And that actually turns out to be the usual form as for the creation annihilation operators. So that's why we can now use these creation annihilation operators to build a Fock space like we did before for the Schrödinger field theory and build the entire Hilbert space of states with different number of particles in it. And the prefactor looks a little complicated, but I had to choose this prefactor, in this case with a box normalization, so that the commutation relation between A and A dagger turns out to be just one as we want for the creation annihilation operator. So it looks just messy and complicated, but the main purpose of this is just to recover the standard commutation relation between creation annihilation operator. And just for the notation, the P, of course, corresponds to the momentum of the particle, like what we used to be in the case of Schrödinger field theory. The only sort of new thing is this EP, which is supposed to be this relativistic energy of a particle of mass m and momentum p. And I didn't write it, but A and B commute, A dagger and B dagger commute, A and B dagger also commute, A dagger and B also commute. So A and B are totally independent sets of the creation annihilation operators, which you can also derive from the canonical commutation relations. So we are not doing that here, but this is the way you actually get the standard commutation relations for creation annihilation operators. And then the rest of the interpretation, I believe, is now completely clear. You have seen it already many times in other field theories. So that's how you get the canonical quantization of the Klein-Gordon field. And right now I'm using this box normalization. The system is in this rigid cube of the side L. It turns out to be actually not very useful thing to do when you want to insist on relativistic invariance, because then the size of the box is fixed in one particular reference frame, but not in the other reference frames. So we eventually switch to delta function normalization of the creation annihilation operators, which is the one you were using in a homework problem. So I come back and talk about that later. But for now, I stick with the box normalization simply because this is something you have seen in other examples already, which probably look more familiar to you. So let's get started with something rather familiar looking instead of jumping right into the delta function normalization, which may look totally new. So I'm trying to go step by step and to get to the delta function normalization later on. But anyway, so any questions about this process of canonical quantization? Okay, well, you have seen this already last week, so probably that's why you don't have any questions right now. Okay, so once you have this mode expansion of phi and phi dot, I can also write out what the Hamiltonian is, and that's again what you're doing homework with the delta function normalization. And if the box normalization, I can just do explicitly do the spatial integral and write everything in terms of creation annihilation operators. And that turns out to be this simple form. So once again, A dagger A is a number operator. B dagger B is another set of number operators. And both of them come with energy EP. So I have two sets of harmonic oscillators with the same energy for both of them. So this is the point you realize that there's something important about having these two sets. I have two creation annihilation operators, A and B, but they have the same energy for a given momentum P, and energy is P squared C squared plus M squared C to the fourth square root. So what that means is that the particle you can create with this A dagger creation operator, and the particle you can create with the B dagger creation operator have the same mass, exactly the same mass. There's no choice here. They have the same mass. And which is, of course, not surprising because only parameter we have in this Lagrangian is M. We know C, we know H bar. The first term doesn't have any parameter, so M is the only parameter in town. So it's not a surprising thing that both of them end up having the same mass. But there's something important about this fact that they come with the same mass. So that's the thing I'd like to discuss on the next slide. But anyway, so this idea of working out Hamiltonian, and that's something you have done, of course, with the harmonic oscillator. And then by plugging in A and A dagger into X and P, you obtain H bar omega times A dagger A. That's exactly the same exercise we are doing here, except that it comes with these different momentum modes. So conceptually, that's exactly the same calculation. All right, any questions about this? Yeah, so I suppose this is now a well-oiled machinery that you have seen many times from the Schrodinger field theory and the vector potential. Okay, so Hamiltonian now makes sense. And this is when we'd like to talk about this conserved current I mentioned earlier. So this is a definition of the current. And it's easy to verify that it is conserved, namely that for divergence of J mu vanishes. And again, you can sort of check this by your eyes. So when you take four divergence, one piece cancels out, namely that when this derivative acts on phi star for the first term, that gives me del mu phi star del mu phi. And if I act the del mu on phi for the second term, I again get del mu phi star del mu phi. So those two contributions cancel. The piece that doesn't cancel right away is when del mu acts together with del mu that's already there. Then you contract the mu indices, so the derivative now becomes a box. So I end up getting phi star box phi minus box phi star phi. But using Klein-Gordon equation, box phi turns into m squared c squared h bar squared phi. So both terms end up being m squared c squared h bar squared times phi star phi. This one also is m squared c squared h bar squared times phi star phi. So then they cancel. So this fork current is indeed conserved by taking four divergence, the space-time divergence of it. And what that means is that this is a continuity equation now, namely the time component with time derivative, and spatial component, its divergence, would add up to 0. So that's the continuity equation. And therefore, spatial integral of the time component is something that's conserved. And whenever there's a conservation law, there's an underlying symmetry for it. And underlying symmetry is something you have again seen before, namely the symmetry of changing the phase of phi does not change this Lagrangian. And that's what actually leads to this conservation law. So, as I said already, once you have this conservation law, I take the time component of this fork current and do a spatial integral of it. And that quantity n is now time independent. So this is now a conserved quantity. And I am asking you to work out what this quantity n is in terms of creation annihilation operators. Again, not in box normalization I'm doing here, but with a delta function normalization. Then you find that this conserved quantity n turns out to be the difference of the number operator between A creation operator and the B creation operator. And this is actually a demonstration that A and B have opposite charges. And in fact, if you would like to couple this Klein-Gordon field to electromagnetism, and you have already seen how to do it because the gauge invariance forces you to change this derivative into covariant derivative. There's no ambiguity. There's a unique way of doing so. Then from that Lagrangian, you can identify the electric charge of the field phi, which turns out to be actually nothing but this current. So this n, when you actually introduce electromagnetism, has the meaning of electrical charge. So E times n would be electric charge of this field. So the fact that there is a minus sign in between means the particle created by A and particle created by B have opposite electric charges. So this is the place where you first see the sign of something we call antimatter, namely that particle created by A, let's say, is a matter particle. Then the particle created by B is an antimatter particle. We have already seen on the previous slide that they have exactly the same mass, but now we see that they have opposite charges, hence antimatter. So if you have a particle of mass, say 1 kilogram, then antimatter particles also have mass 1 kilogram, but they have opposite electric charges, one positive or one negative. So that's the idea of antimatter. So what you see here is that complex Klein-Gordon field describes a spin zero particle, and we actually talk about the spin in a couple of slides. It's a spin zero particle, but has both particle and antiparticle in it. And so phi field contains the annihilation operator of the particle and the creation operator of the antiparticle. And it also makes sense. If you annihilate a particle, you decrease the charge of the system by 1 unit. If you create an antiparticle, you increase the charge by the opposite sign, which is the same thing as decreasing the charge by 1 unit. So both A and B dagger changes the charge of the state by the same amount. And the same goes with the phi dot. A and B dagger come together. When you look at the phi dagger field operator, then you have A dagger and B coming together. A dagger would increase the charge by 1 unit. B would decrease the charge by -1 unit. So both of them end up increasing the charge by 1 unit. So that's how they can come together. So you see that A and B are particle-antiparticle with same mass and opposite charges. So that's what we learn from this exercise of writing out this conserved charge N. And that's what I'm asking you to do as well in a homework problem. Any questions about this? Benjamin?
Could you repeat the original motivation for these two different operators when we first quantized the field? Was it just because it's a complex?
That's right.
field?
So I'm going to actually show you what happens when phi is a Hermitian or real field in a moment. But so far, the phi was a general complex field, so I'm not allowed to take this B to be the same as A. If I do so, then I find this whole thing to be Hermitian operator, but phi was not a Hermitian operator, so that actually violates the non-hermiticity of the field phi. So I'm not allowed to take B and A to be the same. So I have to keep A and B separate to allow for phi being complex. And so that's why I had to introduce two sets of the harmonic oscillators A and B, which turned out to be important because you have distinction between A and B in terms of their charges. So at the end of the day, it made sense that we had to keep A and B separate from each other.
I see. Thank you.
Okay. Any other questions here?
I just had a general question about
Go ahead.
About the Dirac equation. So I guess how does that stand apart from the Klein-Gordon equation that we're working with? Because I've also heard the Dirac equation can also from that you can derive like the existence of antimatter. So
Right, that's right. So Dirac equation, what comes actually later, hopefully today, and Dirac equation describes particles of spin 1/2, and here Klein-Gordon field describes a particle of spin 0. So that's the main difference between the two. And it turns out that there's also a difference in statistics. The Klein-Gordon field, as you saw, we use the commutation relation. That means that we implicitly assumed already that it's a boson. It turns out that if we got this to be anti-commuting, namely a fermion, we actually run into problems. And I'm going to mention that in a couple of slides. So this has to be boson. On the other hand, in the case of the Dirac equation, Dirac field, it describes spin 1/2, and we are forced to quantize it using anti-commutation relation to get a positive definite energy at the end of the day. So it has to be a fermion. So spin 0 particle described by Klein-Gordon field is a boson. Spin 1/2 particle described by the Dirac field is a fermion. So you have two differences here, difference in spin and difference in statistics. Does that answer your question, Sahil?
yeah, definitely. Thanks.
Okay, good. Thanks for asking that question too. Any other questions here?
Yes.
Oh, sorry. Go.
Thanks.
Go ahead.
So we can show that the forward divergence of the current is 0, but I'm just wondering, like, how does the conservation of the 0th component of the current follow from that?
Yeah.
The conservation
So,
of n.
right. So this del mu j mu vanishing, if I had written out explicitly in terms of time and space, would basically look like the time derivative of the time component plus divergence of the spatial components add up to 0. So if I take this spatial integral of the time component and take time derivative of it, then this time derivative of this time component can now be written in terms of divergence of the spatial components. So this integrand now turns into the divergence of the spatial components. And to the extent, as we always do, drop the surface term, then by integration by parts, it becomes a surface term which is drop. So then you find that this quantity n is independent of time, and therefore it's conserved. So this forward divergence vanishing immediately means that the spatial integral of the time component is independent of time, and therefore is conserved. So that's the argument I used over here.
Okay,
Does that
thanks.
answer your question? Okay.
Yeah,
good.
yeah, thanks.
And somebody else also had a question.
Yeah. I was just wondering if you could go through again, like the A and B dagger in 5x, like they both raise the charge. That sort of segment. I'm not sure I
Right.
totally followed that part.
Yeah. So A operator creates a particle of charge 1 using this n operator, right? And B operator creates the particle of charge -1. And so what I'm checking here is that because A and B dagger appear together in this field operator phi, I wanted to do a consistency check that it is consistent in terms of charge assignments. So what I was telling you is that A is an annihilation operator of particle of charge 1. So if you act A on a state, you remove particle of charge 1, so charge decreases by 1 unit. On the other hand, this B dagger is a creation operator of a particle with charge -1. So if you act B dagger on a state, then that would increase the charge by -1, namely that you decrease the charge by 1. So both A and B dagger do the same thing as far as the charge of the state is conserved, namely that both of them change the charge of the state and by reduce it by 1 unit. So that's how we see the consistency, namely that A and B dagger to be part of the same operator phi, because they change the charge by the same amount, even though they refer to different particles.
Okay, that's super helpful. Thank you.
Okay, good. Well, thank you for asking for clarifications. Any other questions at this stage?
Yeah. So if I'm
Go ahead, George.
remembering the homework problem statement
Mhm.
correctly, if we use the delta normalization for these
Mhm.
mode expansions, the exponentials pick up a time dependence.
Right.
Is there a physical significance to that?
Yeah, so actually, so the time dependence has nothing to do with actually delta function normalization. It has more to do with switching to the Heisenberg picture. So as you remember so far, we have been always using Schrödinger picture. So states evolve in time, but operators don't. So that's the picture we always used. That's why in mode expansion, there's no time dependence in it. But once you actually study the relativistic quantum field theory, which we just started, then it makes more sense to go to Heisenberg picture, because if an operator depends on space, we'd rather treat space and time on equal footing to be consistent with the spirit of relativity, then we'd rather have time dependence of the operator together with spatial dependence. So the Heisenberg picture is much more natural. And so far we've been using Schrödinger picture. That's why I have to discuss the mode expansion of phi and phi dot separate from each other, because they are different operators. One is the coordinate, another is the momentum. So that's why I had to keep them separate in this mode expansion. But once I go to Heisenberg picture, the phi depends on time anyway. So phi dot is just time derivative acting on a field operator. So that actually saves my time as well. I don't need to write phi and phi dot independently. I just write phi and I'm done with it. So it turns out that switching to Heisenberg picture makes things a lot more transparent and easy to deal with. And that's the picture I already used in the homework problem. So having time dependence is not about changing normalization from box normalization to delta function normalization, but rather has to do with the fact that I'm switching over the Heisenberg picture actually soon in the next few slides. Does that answer your question, George?
Yeah, that makes a lot of sense. Thank you.
Okay, good, good. Any other questions? I really welcome questions, as you all know. Is everything okay? Okay, go ahead.
I just had
Hi, Anna.
a question. Hi. So does the n in this case still have the this interpretation as like the number operator, even if we have like a minus sign between the antimatter and matter terms?
So it does have the interpretation as a number operator, which is exactly the next slide, but you have to actually interpret this way. So n is the number of particles minus number of antiparticles. And so talking about this combination actually makes sense, because as we will discuss later, once you have matter and antimatter, you can talk about a process where you create a pair of particle and antiparticle. So when you actually start with nothing and you have only energy, for example, photons or something, then you have n equals 0, because number of particles is 0, number of antiparticles is also 0, 0 minus 0 is 0. That's the initial state. But sending in, for example, 2 photons, you can create a pair of particle and antiparticle. And then you have number of particles being 1, number of antiparticles also being 1. 1 minus 1 is 0, and so it's still 0. So even though you change the number of particles because you created one, you also change the number of antiparticles because you created one. This combination n doesn't change from initial state of 0 minus 0 to the final state of 1 minus 1. So this n is a conserved quantity, as we already talked about, so it never changes. But because there's a minus sign between, now conservation of n allows for the pair creation of matter and antimatter particles, or annihilation of matter and antimatter back to nothing. And we know such a process happens. And I'm going to actually talk about some examples of the creating antiproton and positron later on. And so this certainly does have the meaning of the number operator, but specifically this minus sign is important in such a way that this n is conserved, but nonetheless, you can create a pair of matter and antimatter, or you can let matter and antimatter annihilate. So that's why this minus sign is actually important. N is conserved, but number of particles can change. Number of antiparticles can also change, but only in such a way that difference never changes. Does it make sense?
Yeah.
Okay. Any other questions here?
I was just curious as to why n is equal to the integral of the momentum over, or no, the current, sorry, over like space. Is it by the, I forgot the law, but the derivative of the negative derivative of the density is equal to the current? Is that like the basis of that, or?
Let's see. So this J mu defined this way is the 4 vector. So I have time component and spatial component. And they also satisfy this 4 divergence vanishing. So the so this is what is called the current conservation law. And this is the same thing as the continuity equation we talked about in the case of Schrodinger field. So time derivative of something, density, plus divergence of a vector vanishes. So that's a continuity equation. And whenever you have a continuity equation, then this density integrated over space gives you the conserved quantity. And the reason being that the time derivative of this, you can rewrite the integrand in terms of the divergence of a vector, which becomes a surface term, which I drop, so that vanishes. And that's how you can learn that the time derivative of this quantity vanishes, and therefore it's conserved. So the main point here is that once you have this 4 divergenceless equation, namely the continuity equation, you can always define a conserved quantity by taking a spatial integral of the density, which is the time component of this current. So that's a general rule.
I see. So the first component, the 4 vector, is actually the current, or the density, and the other 3 spatial components are the spatial components of the current.
Right.
Oh, so J consists of both the current and the density, as opposed to
That's right.
Oh, okay. That makes more sense.
And if you, for example, talk about the electric current density, then again, that you have the 4 vector, and the time component of that is the charge density, and spatial component is the current density, and they form a 4-dimensional vector together. And when you take the charge density and do an integration over space, of course, you get the total charge. That is something we know that's conserved. So it's the same idea. Okay, I hope that makes sense, Sahil.
Yeah.
Any other questions here?
Yeah. So what happens if you apply the annihilation operator for the matter on ket 0 state, like 0 being the number of the matter? Would it?
Can you say that again? I'm sorry. The 0 state is what? Not vacuum state?
Like previous regular field theory that we've been dealing with, we had it like the condition that the annihilation operator acting on ket 0, where 0 is the number of the matter particle, makes it 0. Right. And in this case, because we have the antimatter combined in the system, would it bring it to like -1 in matter, which creates the antimatter, which brings it to
I see. Yeah.
What happens there?
Yeah, the answer is no. So you still have this vacuum state or 0 ket, and when you act annihilation operator A on it, you get 0. And also, when you act the annihilation operator B on it, you still get 0. So the 0 ket is a state where number of A particle and number of B particle both vanish. So in this case, n is 0 minus 0, and that's the 0 ket. And on top of this, you can keep acting the creation operator on that. Then you find A particle to get created, B particle to be also get created. But you can also define this n, which is the difference between them, which may vanish even when the particles do exist. But it's not the same thing as 0 ket. if you have the same number of particles and antiparticles, you have energy because each particle carries some energy. So that's different from the zero ket you start out with, which is the vacuum state. Am I answering your question?
Yeah. So does that mean the definition of the zero ket is different from what we had?
No, it's the same. The definition of zero ket is still the state that gets annihilated by the annihilation operators. It's just that I have two sets of annihilation operators, A and B, and a zero ket is annihilated by both of them.
Okay. I see. That makes sense.
So even though I call this number operator, you can think about the number operator of A alone. Let's say that's NA. Number operator B alone, let's say that's NB. And when you start with a zero ket, NA and NB are both zero. If you act creation operator on top of it, you can have NA and NB of whatever number you like. And so you can define these individual number operators, but that's not conserved, it turns out, because you can create a pair of particle and antiparticle. You can change NA by 1, but NB also by 1. And that process actually does happen. So NA and NB individually is not conserved, but NA minus NB is conserved. And that's this total number operator N. So this N has this minus sign, and that's why it's kind of confusing. But the reason I define this quantity N is because this is the conserved quantity. And NA and B individually is not conserved. That's why I'm defining this difference between NA and B, because it's a useful quantity to have because it's conserved.
Okay, that makes sense.
Okay?
Yeah, thank you.
Good. Any further questions? All right. So this is the point when I put in an extra requirement that phi is a Hermitian field. And we are looking at the complex field phi on general grounds because the field can initially be complex. Schrodinger field is a complex field as well. But let's say we put in this extra requirement that phi is real. Then we have to rethink a little bit about this mode expansion because phi now has to be real. So what that means is that when I take the Hermitian conjugate of the first term, that needs to become the same as the second term to make sure this is Hermitian. So this is when I see this extra requirement that the B operator has to be the same as A operator so that field is Hermitian. So when you have a real Klein-Gordon field, as opposed to complex Klein-Gordon field, then I have this extra requirement that A and B operators are the same. And the same requirement applies also to phi dot. And here, the Hermitian conjugate of the first term is the negative of the Hermitian conjugate of the second term, but there's an I in front. So as a whole, this is again a Hermitian operator. So this looks much more similar to the harmonic oscillator in quantum mechanics, where X is A plus A dagger, and P is I A minus A dagger. And because X and P are Hermitian operators. So this is much more closely related to the standard harmonic oscillator in quantum mechanics. But now that A and B are the same, which means that the matter and antimatter are the same. What that means, though, is that when you say phi and phi star are the same, because now it's the Hermitian field, if I said phi star to be the same as phi, then the first term in this current operator becomes the same as the second term, and they cancel. So this is identically 0, which actually makes sense, because if A is antimatter of itself, the matter and antimatter should have the opposite charges, but if they're the same thing, the only thing it can be is 0, namely 0 is the same as negative 0. So real Klein-Gordon field ends up describing a particle which is antimatter of itself. And as a result, it has to be electrically neutral. And you may say that, oh, that's crazy. How can matter and antimatter be the same thing? But at least you have seen a particle which is the same as this antiparticle, namely a photon. And photon is an antiparticle of its own because it's a real field. The vector potential is real. So that's very much similar to Klein-Gordon field with this hermitsticity requirement because it's real. And once you have a field that's real, that means you are talking about a particle which is the antiparticle of itself. And such a field has to be electrically neutral. And in nature, to the extent we know, there's only one such particle that is described by the real Klein-Gordon field, which is the Higgs boson. And we discovered the Higgs boson at the Large Hadron Collider at CERN in Europe, and we know it's electrically neutral. So it is described by the real Klein-Gordon field. We also have measured spin by the effort of our friends working on Atlas collaboration. We know it's spin 0. So the Higgs boson is really an example of a particle that is described by a real Klein-Gordon field, and it's electrically neutral, and it's antiparticle of its own. And so it's actually not crazy. We have seen such a particle. Both photon and Higgs boson are the same as its antiparticle of itself. And in such a situation, we use real field to describe them. So just to recap, if you have a complex field in general, then you have particle and antiparticle. They have opposite charges. They are different. But if you have a real field, you have particle and antiparticle the same as particle. So it cannot have electrical charges. It has to be electrically neutral. And then you do have such an examples of particles like photon and Higgs boson. So this is the answer to some of the questions you have asked. And so what happens when you have the Hermitian field? And this is what happens when you have a Hermitian field. You have a particle which is an antiparticle of its own. Okay, any questions about this? I'm sure there are some questions. No?
So since this general form that we derive for the real Klein-Gordon field is very similar to the same one we derive for the photon, what is, I guess, the fundamental distinction? Is that we derive this from like a matter Lagrangian, whereas the other one was from electromagnetism Lagrangian? Is that part?
Well, yeah, so that's one difference. But the main difference, though, is that in the case of photon, we use the vector potential, which is the part of the 4 vector. So the field itself carries an index mu, while the Klein-Gordon field doesn't have any index. So we call this kind of field a scalar field because it doesn't have any index. It doesn't transform under Lorentz transformation. On the other hand, the vector potential, together with time component and vector spatial component, it's a 4-dimensional vector. And under Lorentz transformation, it changes from one reference frame to another. So that's the difference between Klein-Gordon field, which is scalar field and describes spin 0, versus the vector potential, which is 4-dimensional column vector and describes spin 1. So whether the field transforms under Lorentz transformation or not makes a difference between the Klein-Gordon field and electromagnetic field like the photon. Does that answer the question, Sahil? Okay.
Yeah, it does. Thanks.
Any other questions? All right. And so let me mention why this is a spin 0 particle. So using this mode expansion of creation annihilation operator, we start with this ket 0, which is annihilated by annihilation operator in response to UK's question, I guess. And then you can create one particle at rest. So here, the argument 0 means momentum is 0. So I have created a particle at rest. And this also has one particle in it. So if I define the number operator for a particle alone, then the eigenvalue is 1, which is not conserved, as I mentioned earlier. But anyway, this has an eigenvalue 1. So for the one particle state with a 0 momentum, this is the only state I can create. And if this particle had spin, J, then the particle at rest should come with 2J plus 1 states, right? Because that's how many states there are once you have the total angular momentum J. But here there's only one state. So that's really a good sign that this is actually a spin 0 particle. And because when spin is 0, J equals 0, then 2J plus 1 is 1. And indeed, there's one state. So this is one way you can check that we are talking about spin 0 particle. And as I said already, that in nature, we know only one particle which has this property, namely the Higgs boson. And as the name says, of course, it's a boson. And so one can ask the question, can you actually instead use anti-commutation relation to quantize this theory and get a fermion out? But if you want to actually treat phi as an anti-commuting variable, then looking at the first term, the phi anti-commute, if I switch the order between them, I get a minus sign. But the term looks exactly the same as before, namely that this combination has to be 0. The same is here too. I have phi as a phi squared. If I interchange two phi's, then I get negative phi, which means phi squared is the same as negative phi squared, namely it's 0. So you find that this action is identically 0 if you actually assume that this is a fermion. So, it's not a consistent theory anymore. Action identically vanishes. No, you don't gain anything. And I'm not actually showing it on a slide, but it turns out that it actually, if you try to quantize this theory as a fermion, it violates causality too. Namely that any observable, which is separated by space-like distance, namely that when from going from one point and the other point, and you have to go at a speed faster than the speed of light, then you call that distance as space-like. You can never reach that point. But if two operators don't commute, then you cannot simultaneously measure these two quantities, even though they are not causally connected. And that's when you run into a inconsistency of the theory. So it turns out that when you try to use anti-commutation relation to quantize Klein-Gordon field, you violate causality because two operators at space-like distance do not commute. So it turns out that using boson as a way of quantizing Klein-Gordon field is necessary. We cannot regard this as a fermion. So this is the beginning of the statement called spin statistics theorem, namely that if a particle has an integer spin, in this case, the spin is 0, that's an integer, then you have to quantize the field as a boson. The fermion would lead to inconsistency. Instead, if you have a particle with half-odd spin, like spin 1/2, and that's the case of the Dirac theory, we'll come back and talk about later, you have to quantize it as a fermion. And this is something we know, at least empirically. The Higgs boson is a boson with spin 0. Photon with spin 1 is a boson. We know that. We talked about helium-4 atoms, which has 2 protons, 2 neutrons, 2 electrons. So you have even number of fermions in it. So as a whole, it behaves as a boson. But we also know that the helium-4 atom is spin 0 as a whole. So it still follows the same rule, even though it's not an elementary particle, it's a composite object, but the spin is integer, 0, and it's a boson and undergoes the Bose-Einstein condensate. We know that. But in the case of the fermion, we also talked about helium-3. In this case, I have 2 protons, but only 1 neutron and 2 electrons around it. So you have odd number of fermions in the system. So as a result, whole thing is a fermion and spin is 1/2. So it still follows the same rule, namely that for spin 1/2, which is half odd, the whole object has to be a fermion. So that's the spin statistics theorem. And as you see, we know many examples already, and all of them follow this spin statistics theorem. And at the time of talking about Schrödinger field theory, which is non-relativistic, whether you regard the field as a boson field or fermion field was up to us. We could choose it. We could choose either way. But once you go to relativistic quantum field theory, then that's not a free choice anymore. It's already fixed by the spin of the particle. If you have integer spin particle, it has to be boson. If you have a hat-odd spin particle, it has to be fermion. So we learned something non-trivial here. What used to be arbitrary is now predicted. So relativistic quantum field theory has more predictive power than non-relativistic theory because it tells you something about the relationship between spin and the statistics of particles. So this is the theorem called spin statistics theorem. I mentioned how that comes about very briefly here, that the Klein-Gordon field has to be quantized as a boson. Same argument applies to electromagnetic field, has to be a boson. And we will talk about Dirac field later on, then it has to be quantized as a fermion. Otherwise, you run into a different kinds of problems. And I'm going to mention that hopefully later. Okay, any questions about this?
Bosons and fermions are like defined at like fundamentally just by their commutation anti-commutation relations.
That's
right.
Right.
I see.
And
yeah,
go ahead.
Go ahead. Oh, I was just gonna say, yeah, I also thought like the spin statistics also define the bosons and fermions, but this is actually a theorem. It's not the definition of what defines a boson or fermion, right?
That's right. Yeah, this is the theorem. So the theorem is that if you start with a quantum field theory, Lorentz invariant quantum field theory, where the field has integer spins, then you have to use canonical commutation relation to quantize it. Otherwise, you run into problems. Then once you use canonical commutation relation, as you have done many exercises by now with the Schrodinger field theory, your wave function, multi-particle wave function, turns out to be automatically symmetric, and therefore it's a boson. And if you start with a Dirac field, which is an example of half-odd spin particle, then you use anti-commutation relation to quantize it. And that you have to do it, otherwise you run into problems. And as again, you have seen in the example of the Schrodinger field theory, once you have an anti-commutation relation, then multi-particle wave function is automatically antisymmetric. And that is the definition of being a fermion. So the field has a definite spin, then a field of definite spin would force you to choose one particular statistics. The other one doesn't work for you. And once, whether you have chosen commutation relation and the commutation relation, that tells you whether the wave function is symmetric or antisymmetric, and therefore whether the particle is a boson or fermion. So that's the theorem. So it's not meant to be tautology. It really has a cause and consequence. Is that okay?
Yeah.
Any further questions here?
So, I guess we know that J in this case, like, is the angular momentum because it creates that, it generates that symmetry, like the angular, the phase symmetry.
Yeah.
So, or is it like the opposite way around, that we know that it is the angular momentum, so we know it generates that symmetry, or we only interpret it as the angular momentum because it generates that symmetry?
That's a very good question, Anna. And I didn't do it on slides because it's a little bit messy and complicated. But of course, angular momentum is conserved as a consequence of the Noether's theorem based on the rotational invariance of the system, right? So because system is rotationally invariant, you find angular momentum being conserved. So using rotational invariance of this action, you can derive, again, a conserved current, which corresponds to angular momentum conservation. And if you actually write this out explicitly, you find that the angular momentum of the system has only orbital angular momentum, but nothing else. And if the angular momentum has orbital angular momentum, but nothing else, which means that there's no spin, so that's the way you can verify that indeed this field describes a spin zero particle. And I'm not doing it on this slide. That's why I'm actually relying on this rather indirect argument based on the number of degrees of freedom. But that's the more explicit way of showing why this field actually describes spin zero. It's just that it's technically more messy, and that's why I'm not doing it. So I am sorry about that, but that's something you can actually, in principle, do. And I may try to actually put that down explicitly in the lecture notes. Right now, it doesn't have it in it, but I can try to put that in. Is that okay, Anna?
Yeah, that makes sense.
Okay. Any other questions? Okay. So this is when I introduce this relativistic delta function normalization. The box normalization requires you have a fixed box with a fixed side as your space. And if you change the reference frame, that box is moving. So whole concept is not Lorentz invariant. So we'd rather not do it. And for some practical applications, box normalization can still be useful, but we'd rather not do that. So that's why we tend to switch the delta function normalization whenever we talk about Lorentz invariant quantum field theories. And at the same time, we switch to Heisenberg picture. So who was it asking this question before? I forgot who that was.
That was two things, George.
George, that's right, yeah. So there are two things going on here. We are changing normalization of the creation-relation operator, but we're also changing the picture. And so it may be confusing which is doing what, but let me try to make it very clear here. So the idea is that when you actually look at this Klein-Gordon equation, and Klein-Gordon equation obviously has a time derivative in it. So this Klein-Gordon equation is satisfied only by Heisenberg picture, not in a Schrödinger picture. And you also know this in quantum mechanics. If you have a harmonic oscillator, and if you want to have this Heisenberg equation motion, x double dot plus omega squared x vanishing, and that is satisfied only in Heisenberg picture, not in the Schrödinger picture where x doesn't have time dependence. So the Klein-Gordon equation holds only in Heisenberg picture. But we kind of liked Klein-Gordon equation because this is manifestly Lorentz invariant equation. And that, of course, has to do with the fact that when you have a field, which by definition depends on where you are in space, but in relativity, you like to treat space and time on equal footing, then you'd rather have the field also depending on time, not just on space, but depending on time, which then requires us to use Heisenberg picture. And when you develop perturbation theory, interaction picture is fine too, because there the operator also has time dependence. And as a matter of fact, whenever we actually use the perturbation theory, we use interaction picture at the end of the day, where the field operator satisfies this free field equation, even in the presence of interactions. So using this Klein-Gordon equation is not specific to dealing with the free theory we're doing right now, but even when you introduce interactions, you can still use this free field equation in the interaction picture. And then the field phi depends both on space and time. So we can treat space and time on an equal footing that way. And that is the preferred choice in relativistic quantum field theory. So we are switching here to the Heisenberg picture. And if you don't have interaction, Heisenberg picture and the interaction picture are the same because you're using only H naught. You don't have V part of the Hamiltonian. So you can regard this either Heisenberg picture in free theory or interaction picture in interacting theory. But either way, this field operator satisfies the Klein-Gordon equation where phi is now a function of both space and time. And if you remember what I discussed way back at the beginning of the semester, I told you that in order to be consistent in relativity, you have to demote space from an operator x, like in quantum mechanics, to parameter x as an argument of the field, because you like to treat x and t on equal footing. In quantum mechanics, x is an operator, t is a parameter. You are not treating them on equal footing. So that's why it doesn't mesh well with relativity. But what we are doing here in field theory is x is now demoted to a parameter so that it is now on equal footing as time as a parameter. And field phi is a function of both space and time, both parameters, neither operators. Phi is an operator, but x and t are not operators. And that's where you see this idea in action. So Klein-Gordon equation is now an equation of an operator phi. Phi depends both on space and time, and therefore it has to be in Heisenberg picture or interaction picture, not in Schrödinger picture where phi operator doesn't depend on time. But switching to Heisenberg picture, now phi has dependence both on x and t on equal footing. Therefore, it can satisfy this kind of the relativistic field equation that's manifestly Lorentz invariant. And that's what we would like to do when we want to deal with a relativistic system. But now that phi satisfies the Klein-Gordon equation, I can immediately write down the mode expansion, because this wave factor e to the minus ip dot x over h bar contains both time and space in it. So x is the 4 space-time vector. P is also 4 vector of energy momentum 4 vector. So p dot x is already et minus p dot x. And that's exactly the wave factor we always see in any wave equation. So E over h bar is the angular frequency, P over h bar is the wave vector. So for any wave equation, we always see this combination, which actually turns out to be Lorentz invariant already. And so the idea is that whenever you have this field operator that satisfies the Klein-Gordon equation, I can immediately put this wave factor e to the minus ip dot x in there, as long as p as a 4 vector squares to m squared c squared. So p squared is a shorthand notation of p mu, which is e squared over c squared minus spatial p squared. That's this definition of p squared as a whole, which is m squared c squared. That's the usual definition of an energy and momentum for a relativistic particle. So once p 4 vector satisfies this equation, and put that into the exponent, and this box is a derivative squared, it pulls out p vector twice, that gives you p squared with a minus sign and h bar squared. And from this energy momentum relationship, that immediately satisfies this equation right away. So Klein-Gordon equation would immediately tell you that phi operator as a function of space and time can be expanded in this waveform e to the minus ip dot x. So using the time-dependent operator actually made things a lot easier, because the phi of x with Klein-Gordon equation immediately tells you both dependence on time and space right away. And once I have this, then in a homework problem, you are first being asked to derive the canonically conjugate momentum. That's 1 over c squared phi star dot. So all you have to do is take time derivative, where time is now hidden in this e times t in the exponent. You pull out minus ip over h bar from the exponent, which cancels 1 power over e. And that's exactly what you're going to do in that homework problem. So using the Heisenberg picture, I don't need to separately write down what the expression of the mode expansion of phi is and what is the expression for the mode of expansion of phi dot is, because I can just go ahead and derive it. So that saves me time, makes things simple, and everything is now manifestly relativistic, because I'm treating space and time on equal footing. The one thing you might wonder, though, is why this specific measure of dqp over 2e. And this is also something convenient in relativistic quantum field theory, because this integration volume, as long as p squared is satisfied as m squared c squared, is actually Lorentz invariant, which you can explicitly verify by doing the Lorentz boost the transformation I mentioned actually last week. So this integration volume is Lorentz invariant. This is wave factor e to the minus ip dot x is Lorentz invariant. That's why we have this annihilation operator and creation operator also in a Lorentz invariant meaning to it. And that actually changes the normalization of the commutation relation. It's delta function, but it also has this additional factor of 2e. But it turns out that this combination of 2e times delta function in momentum is again Lorentz invariant. So this is the way we like to keep space and time on an equal footing throughout the formulation. You actually simplify things a lot because I don't need to treat phi and phi dot independent from each other. I can immediately go ahead and solve the Klein-Gordon equation because phi operator now satisfies the Klein-Gordon equation as a Heisenberg operator. And then I can make every expression manifestly Lorentz invariant. And that's why I'm asking you to use this Lorentz invariant delta function normalization, which is actually good from all respects. But I hope I made it clear which part has to do with the Heisenberg picture, which is really about the time dependence of it, and which part has to do with this delta function normalization, which is trying to make everything manifestly Lorentz invariant. So they are playing different roles here, but together they actually do a lot of simplification for us. So that's why I'm asking you to use this normalization instead. So does that answer your question, George?
It does indeed. Thank you.
Oh, good, good, good. And any other questions here?
Can you explain like a little bit?
Tom, I can't hear you very well.
Oh, sorry. Can you hear me now?
Yeah.
Sorry,
Okay.
I just opened the thing accidentally.
No, I'm asking a question. I'm Ryan.
Oh, right. I'm sorry. Go ahead.
Okay, so just can you like elaborate a little bit why D3P over 2EP is Lorentz invariant? Like because usually we consider about a real space volume like
Yeah.
D to the power 4.
Right.
That is Lorentz invariant, but
Yeah.
it's
So
not varying dy. Yeah. This is,
because P and E together form a Lorentz 4 vector, the first thing you can think about is to do an integration over 4 of them, right? So D3P DE would be Lorentz invariant. And indeed it is. But we have this relation that E squared minus P squared is fixed by the mass. So suppose you put in as a delta function into it. Then using the delta function, you can perform integral over energy. But delta function of P squared minus M squared actually gives you 1 over 2E, and that's how you get this measure. So you can view this measure as actually 4-dimensional integral to start out with, but you put in this requirement that P squared is M squared C squared, and together this requirement volume reduces to this combination of D cubed P over 2E. That's one way you can verify that this is indeed Lorentz invariant.
okay, I see.
Okay.
Thank you. Yeah.
Any other questions? Good. So this is pretty much the end of my discussion. So what you are doing right now in a homework problem, so that's why I'm not actually doing it explicitly here, is to show that Hamiltonian indeed can be written in this form. And that basically gives you an idea that this is indeed creation annihilation operator, and A and B create particles of the same mass, even by the same expression EB. And also this, the number operator is A dagger A minus B dagger B. And this is now guaranteed to be conserved because you start out with the 4 current operator whose 4 divergence vanishes, which is a continuity equation. You integrate the density of, which is a time component of the 4 current, and you find this expression. So once again, you see this fact that A and B have the same mass, but have opposite charges, and therefore they are matter and antimatter. So that's what you learn from this exercise. And so the homework problem, of course, you are supposed to do the algebra, but the reason I'm asking you to do is to really experience with your hands, making hands dirty, that A and B have the particle of the same mass, but opposite charges, and therefore it makes sense to interpret them as a particle and an antiparticle of each other. So I guess that's the end of lecture today. All right, any questions?
Could you just elaborate again for the reasoning for the same mass and the opposite charge
Right.
based on the Hamiltonian number
Right.
operator?
So looking at this Hamiltonian, and this is a number operator of A, this is a number operator of B, and both of them create energy given by EP, and EP is p squared 6 c squared plus m squared c to the fourth. So both of them create particle states of the same mass. So that's the meaning of this Hamiltonian. But what is conserved is only the difference between A particle and B particle. So this is already a good indication that you can create a pair of them, or you can let them annihilate with each other, because that's the way you can conserve the difference of the numbers between them, but not the sum. So the sum can change, but difference never does. And that's the way you can see that this is particle and antiparticle of each other. So same mass, opposite charges, you can pair create, you can pair annihilate, and that's really the feature of particle and antiparticle. Does that answer your question, Phil?
Yeah, it does. Thanks.
Okay. Any further questions? Good. I did watch time today, knowing the mistake the last time. So let me finish on time. All right. So stay well. And I'm sure you're anxious to see the election results. So see you on Friday.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.